Hi everybody, welcome back to Viral Integrals. So today is not an integral, although we will be using integrals to solve it. Today we're going to be proving the Basel result. The result of the Basel result shows up all over the place in mathematics, so it's something we really want to derive so we can use it for later integrals. And we will be referring back to this result frequently. So the Basel result says that the sum of the reciprocals of the squares, 1 over 1, 1 over 4, plus 1 over 9, plus 1 over 16, etc., converges to pi squared over 6. There are lots of proofs online about this. As far as I know, I'm the only one that really shows it this way. So this is going to be new. So keep watching. All right, so what are we going to do first? Well, it looks like we're going to break it up into the sum of odd and even over the odd and even squares, so that the complete sum is equal to the odd part plus the even part. So we label the sum S, the odd part O, and the even part E. Keep track of all these. We are going to be using a lot of intermediate substitutions. All right, so now this step might seem weird, but I told you we were going to be bringing integrals into this. Let's take a look at this integral, the integral from 0 to infinity of the natural log x over 1 minus x squared dx. Let's see, how is that going to help us? Well, let's continue and find out. So let's create an integral j that's equal to the integral from 0 to 1 of the same integrand. And then we'll say that I is equal to j, which is the integral from 0 to 1, plus the rest of it. And now let's evaluate the remaining integral. If we perform the substitution x is equal to 1 over u, then we get du, or dx is equal to negative 1 over u squared du. X, the bounds will change from the bound of 1 will go to 0. The bound of 1 will stay 1, and the bound infinity will go to 0. And let's just note that the natural log of 1 over u is just negative natural log u. And if we perform some simplifications, we can see that the integrand becomes natural log u over u squared minus 1, which is exactly the negative. So now you can see that this integral, the integral from 1 to infinity, is the integral from 1 to 0, which, if we introduce a negative sign, becomes the integral from 0 to 1 of natural log u over 1 minus u squared, which is equal to j. And now we just have the two halves, which are both equal to j. So we can say that I is equal to 2 times j. All right, so now comes the time when we introduce a parameterized function. We're going to let f of a equal the integral from 0 to infinity of natural log x over x squared plus a squared dx, for a greater than 0 for now. And now let's let x equal a times u, so dx is a times du. And therefore x squared plus a squared is a squared u squared plus a squared, which is a squared times quantity u squared plus 1. Plugging that substitution in and simplifying gives us that f of a is equal to 1 over a integral 0 to infinity of natural log of au over u squared plus 1 du. And we know that we can split up natural logs by multiplication. And we see that in this step here. Natural log au is natural log a plus natural log u. So f of a splits into two separate integrals. And now another intermediate substitution variable, k. We're going to let k be equal to that integral from 0 to infinity of natural log u over u squared plus 1 du. So now we have f of a equal to all this stuff right there. And we just say that last integral is just 1 over a times k, because we defined k to be that integral that we had before. And now let's let u equal 1 over v, So du is negative 1 over v squared dv. And plugging that substitution in gives the following. So in other words, k equals negative k. So k has to be equal to 0. And evaluating the first integral, all we need to do is take the standard integral from 0 to infinity of 1 over u squared plus 1, which we all know is pi over 2, and multiply it by the outside constant, natural log a over a. And putting all those pieces together gives us a clean formula for f of a. And this is good for a greater than 0. We are going to be extending this in the next step, though. Now, before using a is equal to I, we have to be clear about something. We're going to continue this, continue the formula using the principal branch of the logarithm, where log of I is I pi over 2. Letting a equals I implies that I squared is negative 1, or a squared is negative 1. Plugging that in, and we see that f of I is equal to the integral from 0 to infinity of natural log x over x squared minus 1, and that should look familiar. And we'll just recognize that x squared minus 1 is negative quantity 1 minus x squared. So f at I is equal to the negative integral 0 to infinity natural log x over 1 minus x squared. So f at I is negative I. Or let's just say that I is negative f at the imaginary unit. And using Euler's formula, which was established in a previous video, and plugging in pi over 2 into it, we see that e to the I pi over 2 is cosine of pi over 2, which is 0, plus I times the sine of pi over 2. Sine of pi over 2, of course, is 1, so that's just I. And that's where the previous statement that log of I is equal to I pi over 2 came from. So just plugging that directly into f of a, we see that f of I is pi times log I over 2i, which is pi times, well, we know that log I is I pi over 2, so f of I simplifies to square root of pi over 4. And therefore, I is equal to negative pi squared over 4. And we know that I is equal to 2j, so we know that j is negative pi squared over 8. Remember that j was also equal to the integral from 0 to 1 of natural log x over 1 minus x squared dx. So now what we're going to do is let g of t equal the integral from 0 to 1 of x to the t over 1 minus x squared dx. That might seem strange, but remember from previous videos, we can take a derivative inside, we can take a derivative of g of t directly, and we'll do that in the next step. Taking the derivative of g directly using the Leibniz rule for differentiation under the integral sign gives the following. You see, if we take the partial with respect to t of the integrand, the only thing that changes is we add a natural log x to the integrand. And then if we evaluate g prime at 0, we will recover j. Now let's recognize the following. We know that 1 over 1 minus x squared can be written like this. In other words, it's the sum as n goes from 0 to infinity of x to the 2n. So we can rewrite g of t like this, and then we can combine exponents to make x to the t times x to the 2n, x to the t plus 2n. And therefore, our g of t is the integral from 0 to 1 of that sum. And then we switch the integration and summation notations, which is valid because there's no problems with convergence either way. So we switch it, and now all we have to do is evaluate the inner integral. The inner integral evaluates like this. Therefore, we can express g of t as a sum. Don't forget it was originally described as an integral. And we can take the derivative of that term by term to get g prime of t equal to that sum. And since we want g prime of 0, we just plug in 0. And we see now that j is also equal to that sum. And we already evaluated the exact value of j, therefore the sum has that value. So now what we have is the sum of the, let's see, this is the reciprocals of the odd squares. The sum of the reciprocals of the odd squares is pi squared over 8. So how are we going to get from there to the sum of the reciprocals of the squares being pi squared over 6? And here we formally state the result. So don't forget, our original sum was what we wanted. It was the sum of the reciprocals of the squares. And the sum is, of course, equal to the odd reciprocals plus the even reciprocal squares. And guess what? We already know the odd reciprocal squares. It's pi squared over 8. Let's take a look at the structure of the even sums. That structure has, it's this. It's 1 over 2k squared, k going from 1 to infinity. I hope you can see that. And then we can do some manipulation. We can pull out a 1/4 from every single one of those. And we see that the even sum is equal to 1/4 of the total sum. So don't forget, our original sum was equal to the odd plus the even. And the odd was pi squared over 8, and the even was just 1/4, 1/4 of the total sum. So we have our total sum equaling pi squared over 8 plus 1/4 of our total sum. That means that 3/4 of our sum is pi squared over 8. So since 3/4 of our sum is pi squared over 8, our sum is pi squared over 6. And that gives the Basel result. The sum of the reciprocals of the squares is pi squared over 6. And just a quick check will confirm that. All right, guys, I hope you enjoyed that, and we will see you next time on Viral Integrals.